Thank you. Let me share my screen. Confirm please if my screen is visible.
Yes, sir. The screen is visible.
Okay. Fine. So in this session, we are going to discuss basically two unsupervised learning approaches. One is dimension reduction and one is clustering. So before I start the dimension reduction technique, let me show you what we are going to discuss in this presentation. So we will begin with some basic statistics. So we will understand that what kind of data properties we need to understand, what is the eigenvalue problem, what is the curse of dimensionality, and how to project our data on subspace. And finally, we will see that how exactly principal component analysis, that is a very popular dimension reduction technique, that how it works. So let us begin with, in general, we are working with some data. So data could be either of 1 dimension, 2 dimension, or in general n dimension. And if we are working with the image, then that could be of n square dimension as well, right? So let x is our feature vector, and individual component of this vector represents some observation. So this might be a temperature, pressure, humidity, wind speed, or anything. And this experiment could be anything, and these xi are the observations, or we can say the attributes. And when we are dealing with the small problems or the problems with smaller dimensions of data, then there is not a big issue. But when data is too big, consider, for example, we have an image of dimension 200 by 200 pixel. It is very small image. 200 by 200 means it's nothing. But if we compute, then it is having 200 into 200, that is 40,000 pixels. So whenever you are dealing with the image of just a size 200 by 200, you have to consider, or you have to process 40,000 pixels. And this could be done for many images, maybe 10 images, 100 images, thousands of images. So computationally, that will be very, very intense. So the dimension reduction technique will tell us that how to remove unnecessary variables from the image. Right? So in that case, that would be x1, x2, x3 up to some x 40,000. So that many dimensions we have in that image. So now when we are dealing with such huge vectors, it is having lots of disadvantages. One, that is very obvious, that computationally that will be very intense. Second one is it will take a lot of time for the training. Third one is it might overfit your model, and so many more. So before we discuss how to avoid or how to reduce the dimension, let us first try to understand some basic mathematics that we need for that. So right now I will be talking the topics which are discrete. You might not find them connected, but at the end, while we'll discuss the PCA, all dots will be joined. You will understand the importance of all this. Right. So x is a one vector having certain numbers, some values. So one is a mean or the average. So this is the formula everybody must be knowing, right? That we have to sum up all the elements of this x. So x1 plus x2 plus x3 up to xn, and divide it by total number of elements. So that will give us the mean of the vector or mean of our data. The second important characteristics about data is the variance of the data. So variance we can compute by subtracting the mean from each element of the vector. So x1 minus mean of this vector whole square plus x2 minus mean of the vector whole square. So we have to take the squared difference. We have to add it for all the data points and divide it by total number of elements. So that will give us the variance in the data. Now these two properties will tell us about data. So let us try to understand why we need both of this. Why only mean is not sufficient, or why only variance is not sufficient. So if we consider this data of 5 dimensions, or we can say we have 5 values in attribute A, all values are 10. So it's very obvious that mean of this vector would be 10. This is our vector starting from this to this. of dimension 5. So we will be doing 10 plus 10 plus 10 plus 10 plus 10 divided by 5. So that will be ultimately 10. And variance of this vector would be 0 because mean is 10. All the elements are 10. So when we'll do this, x1 minus mean square plus x2 minus mean square plus x3 minus mean square and so on. When we run this formula, this will result into 0. So this is one scenario. Let us consider another scenario where my data looks like this. 8, 9, 10, 11, 12. All values are different, but still you see mean is 10. Right? 8 plus 9 plus 10 plus 11 plus 12 divided by 5. So that will be 10. Now both vectors have identical mean, but you see the data or the actual vector is not same. So if we only using mean for assessing the data, then there won't be sufficient. We cannot say anything about the data just by using this mean. But if we look at the variance, then now that would be 8 minus 10 whole square plus 9 minus 10 whole square plus 10 minus 10 whole square and so on. So variance is 2.5. So basically mean will tell us where is the center of the data, what is the center of the data, and variance will tell us that how much on an average data points differ from the mean. Right? So on an average it differs from 2.5. If I go for the next data set, that is 98, 99, sorry, 98, 99, 100, 102. If I compute the mean of this, then that would be 100. That would be 100. So here mean are different. So obviously we can understand that, okay, this data would be centered around somewhere near to 10, and this vector would be centered somewhere around near to 100. So that is very clear. But if we look at the variance, variance is still same. So only variance will not help us to understand the data. Only mean will not help us to understand the data. So we need both. Mean will tell us what is the centroid of the data, and variance will tell us that what is the spread of the data, how far data from the mean. Let me take another example. Here it is 50, 75, 100, 125, and 150. This is our data, 5 elements. You see, mean here are same, 100 and 100. But look at the difference in variance, 2.5 to 1562. So now the data is quite far from the mean. So this will tell us about the spread, and this will tell us about the centroid. Right? So these two properties will be useful while we'll go on. The another important property is to understand the scatter of the data. So for that, we will consider one scenario where we have 3 classes: omega 1 that represents red points, omega 2 having green points, and omega 3 that is set of blue points. Now M1, this particular point, represents mean of all the red points. Mean of all the red points, or we can say that M1 is average or mean of class omega 1. Similarly, this point M2, it is centroid or the mean of class 2. So that is average of all the green points. Now you already know how to compute mean, right? We already have seen the equation on previous slide. And similarly, M3 is the centroid of class 3, that is omega 3. And this black point, which I have represented as a M, that is the global mean. That means all the red points plus all the green points plus all the blue points divided by total number of points. So this is the global mean. Again, I repeat, M1 is mean of red points, or I can say M1 is mean of class omega 1. M2 is average or mean of all the green points, or I can say it is average of data points within class 2. And same I can say for M3. Whereas M is ultimately, I can also write it as a M1 plus M2 plus M3 divided by 3. Right? Or I can add up all the data points, red data points plus green plus blue divided by total number of points. That will give me the global mean. Fine. How to define the scatter? So scatter, as a name suggests, it will tell us that how data is spread. Data is having what amount of spread from the center. So we will define 3 kinds of scatter. One is within class scatter. As a name suggests, it is a within class scatter. That means how much data points are far away from the mean of that class itself. So if I want to compute the scatter of class omega1, then I'll simply compute the variance of this, that how far all these data points from the mean of that particular centroid of that particular class, like this. For this, I will compute in this way. I'll compute the variance for this class, or I will compute the distance of all these data points from the mean of that. And similarly, I will repeat it for this one. So assume that I'm having a C number of classes. So what I'm doing is I will sum up variance of all three classes. So I is equal to 1 to C. That is, this loop will iterate 3 times because C is 3 right now. C is 3. I have 3 classes. X belongs to omega I. So initially I will be 1. So I will be fetching one by one all data points from omega 1 class. So I'll pick up this point, then second one, then third one. So all these will be referred as a X. And I'm subtracting mean from that X. I is equal to 1. So Mi will be M1. So what I'm doing is I'm picking up all the data points, subtracting mean from that, and I'm then taking the square. So ultimately I'm finding the variance, and that I'm summing up. So that will give me the within class scatter. Scatter in this class plus scatter in this class plus scatter in this class. So that is within class scatter. Second terminology is between class scatter. That means what is the separation of class, okay, or how far two classes are from each other. So that we can assess by the distance of mean of every class, that how far they are from each other. See, if one class is here and another class is here, then obviously distance between the mean of these two classes is very high. So we can say that between class scatter is very high. But if two classes are very close to each other, then distance between the between class scatter between these two classes would be very small. So between class scatter we can compute like this, that this is the global mean. So we have to take variance of class mean now. Instead of data points, we will compute the variance of class mean, that is M1 minus M whole square plus M2 minus M whole square plus M3 minus M whole square. That we are doing, and that we are weighting by number of data points into that particular class. So suppose here we have 50 data points in class 1. So here it will go like this, 50 into Mi. So Mi is class number 1. So M1 minus M whole square plus, suppose we have some 25 data points here. So here it will be 25, and that is a class 2. So that will go like this, M2 minus M whole square plus we have some 30 data points in blue class. So that will be 30 into M3 minus M whole square. So that will give us the between class scatter. That will tell us that how far each class from all other classes. That's what between class scatter. And next one is the total scatter. So either we can directly do SB plus SW. That will also be the same like this. Or what I can do is I can compute the distance of each data point from each class to the global mean. So I'll do this. I'll compute the variance in this way now. Or simply I can add up SW plus SB. That will give the total scatter, right? Between class scatter plus within class scatter. So I hope that the definition of mean, variance, within class scatter, between class scatter, and total scatter is clear to you. Is there any question related to this? You can type your questions in chat box. I'll be checking it occasionally. Okay, fine. Yeah, transpose of matrix. If we are dealing with the scalar value, then we have to do square. If we are dealing with the vector, then that would be transpose. That is the meaning of this. Transpose, when X and Mi are actually a vector, we have to do transpose, and then we have to multiply pointwise. But if they are scalar value, we can directly take the square. Good. The another term is correlation and covariance. Assume that we have two observations or two attributes X and Y for some observation. These are the values of X, values of Y. Again, we have 5 observations. Mean of both are 0. Variance in X is 1, variance in Y is 2. I want to check whether there is any relationship between X and Y or not. So there are many ways to assess that. The best one is that you just do the scatter plot. Scatter plot means it's a visual representation of one variable versus other. So I'm just drawing X versus Y. there is a change in variable. Actually, this is X and this is Y. So this 5 data points I'm getting. So visually, I can see that I can fit all those data points through a line, straight line. That means there is a strong correlation between X and Y. If two variables are correlated, then it is very easy to predict one variable from the other. Suppose I want to know that what will be Y for X is equal to -1. So I know the equation of line y is equal to mx plus c. I can simply run the gradient descent and I can find out the slope of this line and y-intercept. And then I will put this x into the line equation. So I can easily get what will be the y for that. This is possible when points or attributes are correlated. But if there is correlation is less or there is no correlation, then it is difficult to predict one from other. Fine. This is a visually, this scatter plot is a visual representation. Visually, we can say that, okay, there is a correlation. What if data points are like this, somewhat away from the line? They are still correlated, but they are not perfectly correlated like previous one. So how to quantify that correlation or the covariance? Okay, that whether they are strongly correlated or they are poorly correlated or there is no poor correlation at all. So how to mathematically represent that or how to analytically represent that? So for that, we have different measurements. One is like a correlation. You can find out correlation between two variables x and y using this formula. This is also known as a Pearson correlation coefficient. That's pretty straightforward. Xi minus x bar and yi minus y bar. See, this you already know. Xi minus x bar, that is the mean of x, and then taking square and summing this. What is this? Variance, right? But now variance is always computed for one variable, remember that, and covariance is computed between two variables. So if I do like this now, yi minus y bar, then simply I'm computing the covariance between x and y. It says that how x and y changes together. That is what covariance. And here I'm simply computing variance in x, variance in y. I'm multiplying that, and then I'm taking the square root. Right? So this is how we can compute the correlation variable. The correlation will be always between -1 and +1. Remember that. Whatever may be the magnitude of input variables, whether they are in 1 digit, 2 digit, or 10 digit, the correlation will be always between -1 to +1. So it is always normalized thing because we are dividing it by the standard deviation. So that will always normalize between -1 and 1. +1 indicates there is a perfect positive correlation. -1 indicates there is a perfect negative correlation. Negative correlation means what? One variable is increasing, other is decreasing. So here x is increasing, but y is decreasing. And that is also with proper slope of -1. Here slope is perfectly +1 because they are perfectly positively correlated. If your data points are like this, then correlation may not be exact 1, but that could be somewhere around 0.9, 0.8. If they are like this, scatter is more. Now see, you will understand why scatter is important. If scatter is more into the data, then the correlation might be 0.6 or 0.7. And if your data is like this, fully scattered, they are scattered like this. In that case, there is no correlation. Correlation would be 0. So in this direction, if data points are related, it's a positive correlation. If they are related in this direction, it's a negative correlation. Let me give one simple example. If my x-axis, y-axis represents, suppose, grade, and x-axis indicates reading hours. So as reading hour increases, there are chances that grade will also increase for any student. So we can say that they are positively correlated. As x increases, y will also increase. Let me take another example of negative correlation. X-axis represents reading hours. Y-axis represents number of hours, sorry, not reading hours, but it is a hour spent on social media, and this represents grade. So if more hours are spent on social media, obviously there are chances that grade will decrease. So this is called a negative correlation. They are correlated, but negatively. Right? So sign is not important, whether it's positive or negative. If variables are related, we can use that property for predicting one from another. Okay. So one is a correlation that we have understood, and the second one is a yeah. So when they are perfectly correlated, see, this is called correlation matrix. In correlation matrix, diagonal variable will be always 1 because this is A, this is B, this is A, and this is B. So correlation between variable with itself will be always 1. A and A is 1. The correlation between B and B is always 1. This represents correlation between variable A and B. So right now it is perfectly correlated, and that is why correlation is 1. If some point would be something like this, deviated from the line, then my correlation matrix might be 1, 1, and this could be 0.9, 0.9. This two will be same because it is always a symmetric matrix. The next concept is a covariance. So covariance, as I said, that when I compute simply xi minus x bar whole square, that is the variance. But when I compute it between two variables yi minus y bar, that becomes covariance. So summation of xi minus x bar into yi minus y bar over all the n data points divided by total number of data points, that will give me the covariance between x and y. So covariance is a measure of how quickly mean of two variables changes together, or how quickly two variable changes its value. So covariance value may not be always 1. Remember that it will not be contained within -1 or +1 or 0 or 1. It depends on unit. What is the magnitude? So your covariance can be as low as -infinity, or it can go as high as +infinity. This is unit dependent, and that is why it is not that good to assess the data. Fine. Whereas correlation is normalizing the relation, and it will be always between -1 to 1. So it is easy to compare data with two data with different magnitudes. Consider age. So age could be between 0 to 100. Right? Hardly a two-digit value will be there. If I consider weight, weight can also be always between 2 digits. Right? Hardly it will go up beyond 100. But if I consider, say for example, price of some product. So price can vary from 2 digit to 5 digit or 6 digit as well. Fine. So in that case, the variance comparison will not be that much relevant because their magnitudes are different. Fine. But correlation comparison you can always do, as it is normalizing our data. Okay. The next topic is eigenvalue problem. Because principal component analysis is all about finding the eigenvectors where you can project your data efficiently. So we will understand how eigenvectors are computed. That's, I guess, it's a kind of repetition. You have already studied how to compute the eigenvectors, but I'll quickly give you the recap. So suppose we have some matrix A. A should be square matrix. That is the requirement of eigenvalue. And if you want to compute eigenvector for any matrix, it must be a square matrix. And we can say that vector x is an eigenvector of A if it satisfies this condition. Ax is equal to lambda x. A is a square matrix. X is an eigenvector. So eigenvector would be like this, is equal to some lambda. So lambda would be some scalar value, maybe 3, 4, 80, anything, into again x. If this condition is satisfied, then we can say that x is an eigenvector of A. Right? And how to compute that? So let me show you one example. That consider A is 1 root 2 root 2 2, and I guess you are familiar with the power method to compute the eigenvectors and eigenvalues. So to do that, we have to subtract lambda from all the diagonal values. So if it is 3 by 3, then there will be one more element. So from that also we will be subtracting it. So we are subtracting lambda from all the diagonal values, and then we have to compute the determinant of that. So that will be 1 minus lambda into 2 minus lambda minus root 2 into root 2. Fine. And when you solve that, it will be lambda square minus 3 lambda is equal to 0. This is a quadratic equation, and when you solve it, we will get two values for lambda. Lambda 1 is equal to 0, lambda 2 is equal to 3. That means two eigenvectors are possible for this matrix. If your matrix is m by m, then there are m different eigenvectors are possible. Let us find out how to find those eigenvectors now. So for lambda is equal to 0, we know that this is the equation for x being an eigenvector for matrix A. So our A is this is our x, is equal to lambda into x, but lambda is 0. So when we multiply lambda with x1, x2, that will become 0, 0. So I have directly written it. Now you simply solve this matrix. So that will be 1 into x1 plus root 2 into x2 is equal to 0. So that will be one equation. The other would be root 2 into x1 plus 2 into x2 is equal to 0. That would be second equation. And when we simplify, we will get x2 is equal to minus x1 by root 2. Now we will consider another eigenvalue. Okay, lambda is known as an eigenvalue and x is known as an eigenvector. So now we will put lambda is equal to 3 in this equation. So now this will not be 0 anymore. Rather, it would be lambda into x. So that is 3 into x1, x2. Right? So this will be equivalent to 1 into x1. Sorry, 1 into x1 plus root 2 into x2 is equal to 3 into x1. So that's the first equation. Then root 2 into x1 plus 2 into x2 is equal to 3x2. That will be the second equation. When you solve it, we will get x2 is equal to root 2 into x1. So we have two equations and two variables. Let us move ahead. Normally, we are interested in finding eigenvectors of unit length. See, whenever you are working in statistics or machine learning, if you have some prerequisite knowledge, then when you normalize data or when you mean centered your data, it will help you to minimize your mathematical computation. It will simplify your mathematical computations. So what we are doing is we will be looking for the unit length eigenvector. See, normally suppose you are given some vector like this 3, 4. So length of this would be 3 square plus 4 square, right, divided by square root of 3 square plus 4 square, something like this. So this may be some 3.28 or whatever. This is not unit length. Okay? Unit length means the length of vector would be always 1. So we are normalizing the length and making it 1. So component of our eigenvectors are x1 and x2. So we are simply doing x1 square plus x2 square is equal to 1. So length of this vector, we are trying to make it 1. So if I rewrite, then this would be x2 is equal to square root of 1 minus x1 square, right? I can rewrite it in this way. From previous slide, for lambda is equal to 0, we have already derived this. X2 is equal to minus x1 by root 2. Let us put this x2 into this equation. Fine. Put this x2 into this equation, which we have just simplified here. X2 is equal to root 1 minus x1 square. And then just to go through the steps and find out x1. So x1 square is 2 by 3. So x1 would be 0.8165. Now put this x1 back into this equation. So we will get x2. So which is minus 0.5774. So if I do this square plus this number square, then that would be always 1. Otherwise, that will shoot. It could be 2, 3, 4, or it can go to up to any magnitude. That will increase the mathematical computation later. So what we are doing is we are already simplifying it. We are normalizing it. Similarly, for lambda is equal to 3, we have another equation. Same way again, I'm rewriting it x2 into 1 minus root x1 square. And x2 I will replace by root 2 x1. And when I simplify, I'll get x1 is equal to 0.5774 and x2 is equal to 0.8165. So we got two eigenvectors. One on previous slide, that is x1, x2, this one, that is this matrix. And the second one is here, that is this one. So as I said that if our matrix is m by m, then we will be having m eigenvectors. Okay? Now see, this is our original data. This we have already considered A and B, if you remember. So if I multiply, now this is our thick matrix. Let us call it as A now. Reduce this. This is A. If I multiply this A with the eigenvectors, then it is converted into this. Now look at this carefully. This is two-dimensional data. This is my first observation. This is second observation. All observations are of 2 dimensions. But when I multiply it with eigenvectors, it is converted into this form. And you see that here all values are 0. So even if I do not consider this, and if I only consider this, then also that is sufficient to represent my data. So ultimately what we did, we have projected our original data on eigenvector, and we have reduced the dimension from 2 to 1. So earlier, my data point was like this. It was falling across the line. After projection, it looks like this. Okay. Earlier, it was on axis X and Y or A and B, but now it is having axis PC1 and PC2. So this is called principal component 1. This is called principal component 2. So what we did, we have, or let me put it in another way. The example will come later on, but still I'm giving it. Suppose this is my data point whose value is 2,3. If I project this data on x-axis, then this will become just a 2. If I project this data on y-axis, then this will become just a 3. Because when I put it onto the x-axis, I'm losing the y component. So that will be just a 2. If I project it on y-axis, I will lose x information. So that will be just a 3. So these two are the standard axes. So I can easily compute what is 2 and what is 3. But assume that I have this kind of axis. And if I project it here, okay, then what value this point will take? If I have some another dimension like this, and if I project this point here, then what value this will take, right? So these dimensions or these are nothing but they are PC1 and PC2. That is our principal component 1 and principal component 2 that we have computed from here. So on those axes, the data will look like this now. This might be a bit heavy mathematics for you perhaps, but I will explain this with the help of diagrams as well. So probably you can easily grasp it. Why we need PCA? The question is now. So see, visually, see, most of the times we are dealing with the pattern discovery, right? That what is the pattern hidden within the data. Now the data could be anything. It may be audio, maybe video, maybe numeric data, maybe image, maybe something else, spectral image or anything. But when we look at the image, the similarity we can observe visually. But how to handle it mathematically or how to identify it mathematically? Fine, similarity is very hard to define, but we know that it is there. You look at these images and you can easily say that, okay, there is some correlation between these images. Right? But how to find out that correlation or how to find those similarities? That is very that is very important to understand, because in real life we are dealing with numerous pattern recognition problems like optical character recognition, face recognition, fingerprint recognition, facial expression recognition, fruit recognition, these, that, and number of such pattern recognition problems exist, right? So how we actually perform the pattern recognition? So consider that you are owing one company and you having 100 employees in your office, and you have implemented some authorization system where all these faces are stored in the hardware. And next day, when some employee is coming, he is standing in front of camera. So camera will capture the image, and that will algorithm will try to match it with all the images. And wherever match is found, the attendance will be marked. Right? That's what the ideal scenario. So what happens? The algorithm will simply try to match the captured image with already stored image. We will call it as a templates. Right? So captured image will be compared with the templates one by one until match is found. Fine. Ideally we assume that there will be a same image, whatever is captured and whatever is stored in database. If they are identical, then there will be a perfect match, and the algorithm will hold, and the algorithm will mark the presence for that, and the person will given the authorization for whatever task he is looking for. But this is having a lot of complexities. When you do this pixel by pixel comparison, now just think about the computational complexities. Let me put it in some different way. Suppose whatever image we are capturing, it is of dimension 300 by 300. All these images are of dimension 300 by 300. So if I'm going to compare it pixel by pixel, okay, first pixel of this image, then first pixel of this, then I will pick up the second pixel of this image, second pixel of this image, and so on. So in general, for one image, I have to do 300 into 300, that is 90,000 comparisons. And I will get some similarity or dissimilarity threshold. Okay? Suppose it is 3, 8, 2, 4, whatever it is, something like this. The difference between these two images is like this. Then I'll compute it with the second image. Again, it will incur some similarity or dissimilarity measure, maybe 388 and so on. So if there are 100 employees, I have to repeat that procedure 100 times. So ultimately, I would be doing 90 lakhs comparisons. Right? I have to do 90 lakhs comparison only for image of dimension 300 by 300 and only 100 employees. Very small organization. Fine. And this is also not a simple, comparison of 3 is equal to 4 or not. Either we are using some Euclidean distance between 2 points, or we may be calculating correlation between something like that. So we are executing some complex formulas, like we have to take the intensity of first pixel minus of this image minus intensity of first pixel of this image, and then we have to square that. So square itself is very, mathematically very intense procedure. Squaring the number, it takes lots of, computational resources. Plus, then we will go for the second pixel of this and second pixel of this. So maybe 128 is the intensity of pixel in captured image, minus 32 maybe the intensity of second pixel into the template. Then we are squaring it. So we have to perform that many squares, that many additions. Then we have to take the square root. So you can understand that impracticality of this approach. This is known as a holistic approach, where we are directly comparing all dimensions of the images, and that is why it will take a very long time, and practically it is not feasible. So the desired approach is that you go for some dimension reduction. Okay, this is known as the curse of dimension, right? When you have a huge high dimensional data, specifically image, any operation is very, very costly. So we will try to represent the image effectively with lesser dimensions, and there comes principal component analysis into the picture. Okay, assume that we have one vector A is equal to 3. When I represent this vector into one dimensional system, then that vector will become a single point in that coordinate system. If I have vector of 2 dimensions, 3 and 1, if I represent this vector in 2-dimensional system, then it will be represented as a point, but it will become a single point. If I have 3-dimensional vector 3, 4, 1, if I represent the same point in 3-dimensional system, then it will become a single point. This can be easily generalized in mathematics. If you have n dimensions vector, when you represent that vector in n-dimensional space, vector will become a point. I hope I'm making this point clear. Visually, we can go up to 3 dimension only, but mathematically, we can go up to infinite dimensions. Fine, we cannot see 4 and 5th and 6th dimension, but mathematically, it is very much possible. Fine. So what I'm trying to say is, if our image is, say, for example, 300 by 300 dimension image we have. So when we convert it into vector, it will become 90,000 by 1 vector, right? So that was a rectangle or square that we have simply converted into one vector. So this is 300 by 300. This will be 90K by 1, 90,000 by 1 vector. When I represent this 90,000 dimensional vector into a coordinate system of 90,000, then this image will be represented as a single point. Right? See here, each axis represents one component, 3. So distance from x-axis represents 3. This one, this is 3. Then y represents 4. So this axis represents y value. This axis represents z value. Similarly, image is a set of intensity values, right? So when we have a 90,000, 90K dimension coordinate system, each coordinate or each dimension will represent the intensity of every pixel. So this may be representing intensity of first pixel. This may be representing intensity of second pixel, third pixel, and finally it is 90,000 pixel. I hope it is clear, right? As ultimately what I want to convey is that if your vector dimension is n, when you move it into the n-dimensional space, it will become single point. That's what I just want to convey. Let us try to understand the concept of projection and how we can reduce the dimension and how many dimensions we should keep. That is very important. You cannot blindly remove dimensions from image. Otherwise, you won't be able to classify them correctly. And if you should not keep unnecessary dimensions as well, otherwise it will overfit your model or it will increase the computation. So let us try to understand with this diagram. We have three classes, red, green, and blue, and I have written their dimension. Assume that these are the sum of the attribute, maybe temperature, pressure, humidity, or whatever it is. Fine, whatever may be the class, maybe say for example, blood pressure, heartbeat rate, and maybe sugar level. Depends on problem, but I'm just taking some hypothetical example. So this three represents class 1, class 2, and class 3. And I'm using a three-dimensional system right now. So they will have a three components, 440, 430, 332, and so on. Now see, if I project all this data on x-axis, so this is my data point 1. I will project it on x-axis. I will get it somewhere here. I will lose my y component. I will lose my z component as well. So that first data point will be just a 4, whatever is the x component there. Similarly, when I project this data point on x-axis, that will also be projected here. I will lose y component and z component. So this will become just a 4. And similarly, when I project this third point here, it will be projected somewhere here. Y and z will be gone. I'm only having 3 here. Same I'm repeating for class 2 and class 3. Fine. So I hope that it is clear. Now what I'm doing is I'm projecting it on axis right now. So now I'm projecting it in this way. So when I'll project this data point on y-axis, I will lose my x, I will lose my z. So data point x will become 4, 2 will become 3, and data point 3 will become 3. So this is 4, 3, 3. Similarly, this would be 2, 3, and 2, 2, 3, and 2. And this would be -1, 0, and 0. That is -1, 0, 0. So you see that by projection, I have able to successfully reduce the dimensions of these data points. This 3 dimension, 10 dimension, 1000 dimension. But when I project it on one axis, I will get one value. But the problem is that when I'm doing this, you see that these two data points are having the same value. These two are having same value. These two are having same value. Similarly, here 3 and 3, 2 and 2, 0 and 0. So what it means, when I project data on single axis, I'm losing lots of information, and hence I will not be able to distinguish them correctly. So I don't know, whenever I'm given 4, I don't know whether it is data point 1 or data point 2, because both are being mapped to 4 and 4. Fine. So I have reduced dimension from 3 to 1. So I have saved the space, I have saved the computation, but I'm losing the accuracy. So what I need to do is, suppose I'm trying to plot it on XY plane. That means I will plot the same data on x-axis. I will collect this value. I will call it as x1. I will project it on y-axis. I will collect that value. I will put it here, and I will call it as a y1. So if I do that, then my data point x would become 4, 4. This would be 4, 3. This would be 3, 3, because I'm projecting on XY planes. So Z component information I will lose. Whenever you do projection, you are going to lose some information because you are reducing the dimension. So right now I'm projecting on plane instead of axis. So I have 2 dimensions now, 4, 4, 4, 3, 3, 3. Here it will be -1, 2, -1, 3, -2, 2. And here it will be 1, -1, 1, 0, and 0, 0. Here dimension of data was 1. Here dimensions of data are 2. But look at here, 4, 4, 4, 3, 3, 3. All points are distinguishable. -1, 2, -1, 3, -2, 2. I can distinguish all the points. 1, -1, 1, 0, 0, 0. I can nicely distinguish this. That means I should not be too greedy to reduce the dimensions such that I will lose information, discriminative information. And I should not be too generous to accommodate the third dimension, which is not important for classification. I hope you are with me. So this 2-dimensional representation is sufficient. So what we did, we have reduced the dimension, and yet we are preserving the discrimination property of the data. So that is what the heart of the PCA, principal component analysis. So this reduction in dimension can be done in 2 ways, either using dimension reduction technique or using feature selection. So under dimension reduction, we have a principal component analysis, linear discriminant analysis, singular value decomposition, ICA, CCA, etc. Feature selection, we have ADA, SFS, SBS, mutual information, and many. the list is big in both the cases. And today we will discuss principal component analysis. So the goal of principal component analysis is to maximize the variance after the projection. So what it means, let me just try to explain you with the diagram. Suppose these are the data points. Red and blue are samples. That could be anything. Fine. Here also same data points are there. If I project them on this axis, then all are projected here. If I look at the variance, that means the scatter. That scatter is less. If I project it on this axis, then you see that the scatter is very high, as well as data points are well separated after projection. But here data points are overlapping. So whenever some new point will come for the classification, and if I project it here, then there will be a confusion whether it is coming from blue class or red class, right? But here there is no confusion. So what PCA aim is, it will always try to find the direction on which if we project our data, then variance would be maximum. So this is the ideal axis, or we can say it is a principal component computed by the PCA, right? This is not that good because here it is overlapping. There could be some different axis as well. When you project on this, you might get some good separation, right? So variance after projecting on each axis would be different. The goal of PCA is to find the axis which gives us the maximum variance, second maximum variance, third maximum variance, and so on. And based on that, we will determine how many dimensions we should preserve, whether we should go for 90,000 dimension, or we should go for just a 50 dimension, or 30, or 5, or 2. Okay? That we can determine based on this variance property. Okay. Let us see how PCA works. PCA assumes that the information is carried in the variance of the feature. See, this is the assumption of PCA. Sometimes it may not be true, but most of the times that is true. That variance is very important, and PCA will always try to maximize that variance of projected data. Higher the variance in the feature, the higher the information carried by that feature. Because see, it conveys the maximum information. It is increasing the variance of overall data. And PCA is a change of variable space only. So it is just looking at the data in different way. So we are very much habituated to look the data into XY plane. So if I look at this point, it may appear as a 3,4 in X, Y plane. But when I change my coordinate system like this, in that case, same point might become 1 and 2.3. Point is same. What we did is we are just changing our coordinate system, and that is why this data looks different. So assume that these are the two different data points, and after PCA, this might look like this. Still data is same, but it appears, in different way because we have changed our viewpoint. So that is what we are trying to do in our PCA analysis, that we are simply changing our coordinate system and then projecting the data so that we can maximize the variance. Can anyone please mute the participant? Anyone from the organizing committee? Yeah, thank you. Let us try to understand PCA with the help of visualization. Suppose you want to implement face recognition system. Right? So these are the faces. Let us call it as X1, X2, X3, X4, and so on. And all Xi's are of dimension n by n. So if I consider it is 300 by 300, then there are 90,000 dimensions of the image. If it's at 100 by 100, then there are 10,000. Keep track of dimension. It is very important when you understand the PCA. All images, I'm considering it as a n cross n. On every slide, I will show the visualization. I will also show the dimensions of the variables. The first step in PCA is to compute the mean of all the data. See, face I have kept because you can easily understand and visualize, but this could be anything. This could be your transactional database. This could be your any kind of measurements. This could be coming from the IoT device. This could be medical data set. It could be any kind of data, maybe voice, maybe text, maybe numbers, maybe tables, anything this could be. But to understand with images is easy. That is why I'm taking this example. So here I'm simply taking the average of face. Suppose you have some rain prediction problem. So you will have attributes like temperature, pressure, humidity, wind speed, and so on. Fine. So you have to sum up all those vectors. If you have 100 days data, then you will be adding all those 100 days measurements. That's it. Right? So first thing is that we need to compute the mean of that. So we will add up all the samples and divide it by total number of samples. So we will get the mean. Again, size will remain same, n cross n, because it's just addition and divided by that number of samples. Next step is we have to mean center the data. That means we have to subtract the mean from each data point. So whatever mean we have computed, we will subtract it from all the xi's. So that is known as the mean centered data. Mean centered data, we will represent it as a xi bar. So xi bar is computed as a xi minus m, where xi is our actual vector or actual data, m is the mean of that. So it will create some ghost kind of images when you subtract the mean from that. And again, the dimension of all images will remain n cross n, because this is just a matrix or a vector subtraction operation, nothing else. So that is not going to change the dimensions. After that, whatever image we have, ghost images, that is right now in 2-dimensional, right? N cross n. That we have to convert into 1-dimensional. So this image will be converted into vector, and this vector will have dimension n square by 1. Okay? So what we are doing is we are simply catching this first row that we are putting here, then we are selecting second column, and then we are putting it after that. Then we are selecting third column, we are attaching here, fourth one, concatenating here, and so on. Finally, nth column we are concatenating. So obviously the dimension of this vector would be n square by 1. So each image will be represented by one column. So you see that this capital X is the thick matrix which contains column format of x1 bar, x2 bar, and xm bar. So now this will represent image 1, image 2, image 3. All are mean centered image, but converted into column format, right? In a 1-dimensional vector format. So this dimensions or number of rows here are n square. And I assume that we have such m images for the training. Okay, we have m images we have for our experiment. So dimension of this x would be n square by m. It is having n square rows and m columns. Each column represents mean centered image. Hope you are with me up to this point. Next, we need to compute covariance of this X matrix. So covariance is computed by multiplying the transpose of matrix with the matrix itself. Okay, so that will give us the covariance. The dimension of X is n square by m. So when you take the transpose, that will be m by n square. So the dimension of this covariance matrix, when you multiply these two, it will become n square by n square. That is very, very high dimensional matrix, because n was 300 by 300. So n square would be 300 into 300, that is 90,000. Right? So this covariance matrix would be of 90,000 by 90,000 dimension. That is impractical to handle by any software routine. So what we can do is, we can simplify this process by inverting that. We can do X transpose into X. So dimension of X is n square by m. So dimension of its transpose would be m into x n square. And when you multiply these two, it would be just m by m. Okay, so C would be m by m. Covariance matrix would be n square by n square. So this is practically not feasible. So we are simply taking the mathematical benefit of mathematical simplification, and we are computing the eigenvector and eigen values of this covariance matrix C rather than COV. M is number of training image. Training images are typically less than the dimensions of the image. So we might have 100 image or 200 image or 300 image. So this matrix might be that small. If we have 100 image, then this would be 100 by 100 matrix. After that, we have to compute the eigenvalues and eigenvector of this 100 by 100 matrix. Now you already know how to compute eigenvalue and eigenvector. I have already shown with the example that we have to subtract lambda from all the diagonal values, then simplify the matrix, compute eigenvalues, eigenvectors. But nowadays, software routines are very powerful. You just call the function, pass this covariance matrix, and it will give you eigenvectors and eigenvalues. So V is a M cross M matrix. See, whatever is the dimension of C, that is M by M, same would be the dimensions of eigenvectors and eigenvalue matrix. This would be M by M, this would also be M by M. Each column in V represents one vector. That means one axis it represents. Normally we had x-axis and y-axis. Now when I pick up this vector, it will represent some vector like this. When I pick up the second one, it will represent some different axis like this. When I plot the third one, it will represent some different directions like this. And when I project all my data points on first axis, it will give me the maximum variance after projection. When I project it onto the second eigenvector, it will give me the second highest variance after projection, and so on. So all these vectors are arranged in decreasing order of their variance, projected variance, right? And that is what we are looking for. So eigenvectors of covariance matrix are linear combination of image space with eigenvectors of L. That means when we multiply our image space X with the eigenvector V, we will get the eigenvector space, that is U is equal to N square into M. But now see that M is still a big number. Suppose we have 100 training images, then our eigenvector would be of 100 by 100 size. My image dimensions are 90,000. If I project them in all 100 eigenvectors, then 90,000 dimension image will become now 100 dimensional image. Okay? So I have reduced 90,000 dimension into 100 only. Fine. That means I have greatly reduced the dimension and still I am preserving maximum variance into the data. That means I would be able to classify the data correctly, or I might be losing very less information. But still, it may be possible that 100 dimensions is still big. So what you can do is, instead of projecting on all M vectors, suppose we have M eigenvectors we have. So we will cut down some of them and we will select only best P eigenvectors, and on those P eigenvectors only we will project our image. So what we can do is, something like this. Now instead of M by N square, we will be selecting first P eigenvectors only. So I assume that this is M by M vector of eigenvectors. It is having M columns. So instead of projecting data on all M columns, what I will do is I will simply reject this one. I will only project on first P eigenvectors. Fine. So the dimension of my projected image would be just a P. So if I will select 30 eigenvectors, then dimension of my projected image will be just a 30 dimension. If you remember, I had 3-dimensional data point. When I was projecting it on 2 axes, the dimension of that point was just a 2 dimension. From 3D, I was making it 2D. Similarly, from 90,000 dimensional image, I'm making it 30 dimensional by projecting it on 30 different eigenvectors. And see, first eigenvector will preserve the highest variance into the data. Second will have second highest variance. Third will have third higher variance. So normally the graph of variance will be like this. So when you project it on remaining eigenvectors, the captured variance will be very, very less. It means they do not contribute to the classification. They do not convey much information. So we can reject this, and from based on this graph, we can select whether I want my image to be 5-dimensional, or I want to make my data to be 8-dimensional or 3-dimensional. That's totally upon us. Right? So what we did, we have projected our 90,000 dimensional data point on 10 different axes or 10 different eigenvectors, and we have reduced it from 90K to just 10. Fine. And when we have a test data, we have to do the same thing. We will subtract that mean from T, and then we will project that T on that our eigenvector matrix, and we will compute the P-dimensional test vector. And then we will find out the distance of this test data from all the stored templates. So if you remember, earlier we had this kind of diagram. All images were 300 by 300, and we were doing 90,000 comparisons, right? And we had one test image. So now instead of comparing 300 by 300 pixels, we just have to compare some 10 pixels. So this image will be represented by 10-dimensional vector. This will become 10-dimensional. This will become 10-dimensional. So we just have to compare 10 points instead of 90,000 points. And still, this will be quite great at discriminating the images. If you think that you are losing information and you are not getting good accuracy, you can increase it from 10 to 20. No harm. Still, it is a great reduction from 90,000 to just 20. Right? So very effectively, we are representing our data in lower dimension. And this is just one demo or the results. That these are the this is the test image. If test image will be present into the training set, then the Euclidean distance or the when you do any comparison, that will be 0. But when train image and test image would be different, suppose image is not present during training, then the difference between test and train would not be 0, but that could be minimum. Based on that also, you can identify the class of that image. So another property of PCA is that you can use it in compression as well. So you can easily do the image compression. And after that, you can reconstruct the image with very limited set of images. So we have already computed. Fine. And whatever test image we have, when you project it on that, so that will be simply a weighted average or weighted addition of all these components. And from that, you can reconstruct the image. So if you use less components to reconstruct the image, your image quality of reconstructed image will not be good. But if you are using more components, the quality of reconstructed image will be better and better. So for compression and reconstruction of image also, PCA is having a very good application. So with that, we are concluding PCA. If you have any query related to PCA, feel free to post it into chat box. Is there any question related to this? Difference between PCA and SVD. See, SVD is a singular value decomposition. PCA will directly project your data into onto eigenvectors. And then if you are projecting it on 10 eigenvectors, it will give you 10 different dimensions of the input. Whereas SVD is a matrix factorization technique where our covariance matrix or whatever matrix we are having, it will be divided into or it will be factorized into 3 different matrices, S, V, and D. Fine. And it is having some different applications. However, you can use it for the dimension reduction, but it will not be as effective as PCA at capturing the variance. PCA is unsupervised learning. Similarly, we have a LDA as well, linear discriminant analysis. That is also very powerful dimension reduction technique, but that is a supervised approach, which also considers the class labels and some assumptions of PCA will be relaxed in LDA. So that is, better compared to PCA. Any other question?
Excuse me, sir. Excuse me, sir.
Yes.
Hello.
Yes. Hello.
Actually, correlation part. How does correlation impact in machine learning model, sir?
Sorry.
How does correlation impact in machine learning model, sir?
Yes. See, when 2 attributes are correlated, then you can simply skip one of the attribute from the training. Assume that you have some experiment and you are recording different attributes. Let's say, for example, attribute A1, A2, A3, A4. Let me give you an example. Suppose it is a student database, and in student database, you are recording the age of the student, weight of the student, height of the student, etc., date of birth of the student. So date of birth and age are correlated. And from date of birth, you can easily calculate the age. So there is no need to use date of birth for the training purpose because they are perfectly correlated. You remove one. Age and weight are also somewhat correlated, not perfectly, but there is somewhat correlation, right? As age increases, weight will also increase. So as they are correlated, you can throw away weight as well. So if attributes are correlated, they are simply adding redundancy in your database. And when you use the entire data set, your model has to train on more attributes. That will take more time and model will not be trained properly. But if you are throwing away date of birth, you are throwing away weight, you are throwing away such correlated attributes, then your data set will become simpler, because now instead of 10 attributes, it is having just 5 attributes. So training will be faster and model will be simpler. That is why we need to first do the correlation analysis of any data set. Next question.
Thank you, sir. And one more question. Hello.
Sure. Yes.
Can you explain the positive correlation and the negative correlation in machine learning, sir?
Yes, sure. I have already explained. I guess you missed it. Say, for example, I take two variables. One is a number of hours we are spending for reading, and grade. So if we read more, we will get better grade. So there is a positive correlation, right?
Okay.
The another one is if we spend more time on social media, so grade will be reduced. So that is the negative correlation. But still you can throw it away. Whether there is a positive correlation or negative correlation, you can throw it away one of the variable, either number of hours or or grade, because they are correlated.
Thank you, sir.
Welcome. Any other question? Yeah, there is one question, dear organizers. What about attendance and feedback? Yeah, so we track the attendance session wise, and the feedback will be given on AICT ATAL portal on last session. Attendance will be monitored from our side. In PCA, why covariance matrix is calculated? See, basically we need to understand that which variables are correlated with each other, right? And if there is a correlation, they will be generating the redundancy. So when we compute that covariance matrix, it will give us the correlation as well, that how one variable is associated with other, and based on that, it will generate the eigenvalues and eigenvectors. And that will help us to determine that which eigenaxis is having the maximum projection and which is having lesser, and so that we can eliminate rest of the dimensions from the data. And that is why we need that covariance matrix to understand how different attributes are correlated.
Yes, participants, do you have any other questions? You can ask right now.
One is in chat box, like day-wise feedback form is also through ATAL portal. No, that won't be day-wise. The feedback you have to fill up only once in the last session, on last day. Fine. So if there is no more question, we can conclude the session then.
Yes, sir. On behalf of all the participants, I extend my heartfelt thanks to you, sir, for delivering such an enlightening session. And you explain all the topics with a very simple explanation and lots of examples. So your insight will surely help us to in both teaching and research. And we are truly grateful for your time and devotion, sir. Thank you so much, sir.
Welcome.
Participants, if you have any other questions regarding anything, you can leave them in a chat here. We'll be answering them as and when possible. And all the questions regarding the session can also be put in the chat box, and we'll contact the expert and get back to you as soon as possible. So I will now officially conclude the day 1 of this FDP here. I sincerely thank everyone present here and all the experts who have contributed their knowledge to us. Thank you, everyone. Thank you so much.
Madam, regarding attendance.
Yes.
Regarding attendance, we should go to ATAL portal or what to do?
No, sir. No, sir. You do not do anything. We'll download the attendance session wise and will put a mark on AICTE ATAL on your own behalf, because attendance mark is only available to the coordinator panel of the AICTE ATAL portal. So we'll do it from our side, so don't worry about it. But from your side, you need to give the feedback on the last day of the AICTE ATAL FDP.
Okay,
And you
thank
need
you.
to, and sir, ultimately three requirements are there. First is to appear in the examination, and you need to get more than 70% marks in the examinations for the certification. Second is you need to attend more than 80% of the total sessions of the FDP. And third thing is you need to provide the feedback on the last day of the session. If three requirements are fulfilled from your side, then definitely from the AICTE portal itself, you will be able to download the certificate.
Okay, madam. Thank you. So
Okay,
day-wise
okay.
attendance marking is not required. Okay, thank
No,
you.
no. So it will be done from our side, sir.
Thank you. Thank you. Okay, clear.
Okay. And in addition to it, we have also created a WhatsApp group wherein we have added all the participants along with the organizers. So if you have any query regarding the sessions or schedules, or you please feel free to put a message in that group. We'll try to solve it from our side at the earliest.
Yes, and
Thank
if any contestant has not joined the group, please join them from the email link provided to you for the WhatsApp group. So you can ask any queries there also. Yes, any query regarding anything?
Email ID and email ID is different than the registration ID. So please try to join the session using the registered ID, because that will help us to put the attendance of your own. Otherwise, you can send an email to us so that. Okay. No, clear? Fine. Fine, sir.
Okay.
Here we conclude today's day. Hope everybody enjoyed it a lot and everybody had the happy learning. So have a great evening ahead to everyone. Goodbye.
Yes. You may leave the session now, everyone. Thank you.
Okay, madam, before leaving the meeting, please send the WhatsApp group link over here.
Yeah, okay.
Okay, okay. Thank you. Thank you.